Welcome to Carbohydrates, Chapter 16, Part 2. So this lecture we're going to be looking at our chiral carbons and our cyclic compounds of our monosaccharides. We left off talking about our optical activity, and we said that the mirror image of these sugars are enantiomers, so they are not the same molecule. So it's the mirror image of it, but we can't overlap it to make it identical. We're going to call a reason why this is because there are chiral carbons in the middle of that chain. So that these carbons we can't twist and turn, so when we take the mirror image of it, we have a new molecule. So to kind of figure out how many new molecules we can form just by switching this H and OH on these center carbons, we have a formula. The formula is 2 raised to the n, with the n being number of chiral carbons. So it's just how many center carbons are in the chain. And that gives us the possible stereoisomers, because I can switch the O and the H. Then I can take the mirror image of all of those, and those are pairs of enantiomers. So let's take a look at an example. So this is aldotetrose, and if I look at this one, I've got 2 carbons in the middle. So we're going to call these 2 middle carbons our chiral carbons. So they're chiral because they've got 4 different groups attached to them. So that means that there's 2 raised to the 2, or 4 possible stereoisomers. So I can take the mirror image of this one, and I've got a stereoisomer. And then I can switch our H and our OH. So I switch spots. Now the OH is on the left-hand side. And then take the mirror image again, and I've got another molecule. So to be able to draw and to see these molecules in their enantiomers, we need to draw our molecules vertically now instead of horizontally. So we're going to find out these are going to be called our Fischer projections, and it represents the 3-dimensional structure of our stereoisomers on a flat page. So instead of drawing our carbons like this, we stick them on a flat page, and we've got our Fischer projection. So what this is doing is that instead of having to draw these wedges and these dashed lines going back, we can just draw it as a flat or as just lines, just to make it easier to see. So we're going to be drawing them like this, but just know that they actually represent the horizontal atoms are coming out of the page, and the vertical atoms are actually going behind the page. So our chiral carbon atom is represented in the Fischer projection as the intersection of these lines. So at the middle, these intersections of all of these lines. So then just to be complete, the bonds that point above the page are shown as horizontal lines. And therefore the bonds that go behind the page, or the curve behind them and below the page, are shown as vertical lines. We said that these vertical ones go back, these horizontal ones come out of the page. Alright, so in these Fischer projections, the aldehyde or ketone that's in these carbohydrates is always shown at the top. So we're always put either our aldehyde or our ketone on the top of these Fischer projections. Let's take a look at an example why these Fischer projections are so useful. To try to figure out glyceraldehyde, this is our conventional representation of it, so in our zigzag lines. But this is kind of hard to see how it's going to react. It's really hard to see kind of what's all in the molecule, because it's just there's so much going on. So this Fischer projection kind of simplifies it, and we draw our vertical and our horizontal lines. I've got my aldehyde on top. We'll always have a CH2OH on the bottom. So this projection now, it's much easier to see that our OH is on our left-hand side, so this would be an L projection, or if it would be on the right-hand side as our D projection. So here an example of those L's and D's again. So for our D-glucose, our OH, our last OH in the chiral carbons is on the right. The last of the chiral carbons, OH, is on the left for our L-glucose. Remember, only the middle carbons here are chiral. Only these 4 here are going to have 4 different things attached to them, therefore creating new molecules if I flip those OHs to the other side. So here's just that written out in words. Our OH is on the right with the D, on the left with the L. What I did want to point out is that there is no correlation between D and L and the direction of rotation. So we talked about that polarized light. One of these is going to go to the left a certain degree, and the other one is going to go to the right, or in the positive direction, a certain degree. There is no correlation between left and right here. So just because the OH is on the left does not mean that the light will actually turn to the left when it's placed in the polarized light. Here are some more D and L isomers. So if we have D-allose, I've got it on the right. And as this notes, it's always the chiral carbon furthest from the C double bond O. So we'll always have a C double bond O up top, whether it's the aldehyde or the ketone. So it's always the chiral carbon furthest from it that we are going to be looking at these D's and L's with. All right. So let's just take a look at some of the more common of these monosaccharides that you would be familiar with. So the first one is our D-glucose. So this is our dextrose, or our blood sugar. So it's the most important monosaccharide in our human metabolism. So I told you before that only one of these monosaccharides or one of these isomers is going to be biologically active. Well, it's only the D one, believe it or not. So only when our OH is on the right-hand side will our body actually be able to interact with it. So these are the only ones that are going to be biologically active. So you'll see that coming up, the ones that we can eat all are going to be D isomers for our body. So speaking of blood sugar, we will be looking more at blood sugar and the metabolism of why some people become diabetics. You will be doing an experiment also about blood sugar and diabetes, since a lot of you will interact with this either in your career or even with your family or friends. It's a very, very common affliction now. So it's kind of good to know what's going on, just so maybe you can help them at some point. So another common monosaccharide is our D-fructose, or our fruit sugars. And it's the most common natural ketose. So notice that our other ones were the aldehydes up top. Here's one of the ketoses. And honey is actually 40% fructose. So why honey tastes so sweet is because of this fructose molecule. Once again, notice it's the D version, so the OH is on the right-hand side. Now, if we take some of these monosaccharides and we change them just slightly. So if I take our ribose molecule and I take away an OH, so I'm going to call it a deoxy sugar. So D meaning you're taking away, so deoxy, you're taking away one OH. So our deoxyribose is taking away that top OH. So if you've heard of deoxyribose before, well, it's part of DNA, deoxyribose nucleic acid. So the D in DNA is our deoxyribose. So we're going to see how this molecule actually plays a part in our DNA. So a few more derivatives of these carbohydrate sugars are an amino sugar. So instead of replacing it with an H for deoxy, we're going to take away the H and replace it with an NH3 to call it an amino sugar. So these amino derivatives in which the amino group is replaced by one hydroxy group. So although you may not have heard of these amino sugars because we don't really interact with it too much ourselves, but it is actually a major component in chitin. Chitin is what the exoskeleton of like arthropods, so your insects, is made out of, or like cell walls in fungi. So it is in the animal world, they use this chitin to kind of keep themselves intact. And the major component of it are these amino sugars. Now a derivative that you may be more familiar with are the alcohol sugars. So this is where the carbonyl group up on top has been reduced to an alcohol group. So they're reducing the sugar and producing an alcohol on top. Now when they do that, our body can no longer process this molecule. So we have to have this exact molecule to be able to process it. So by taking away that aldehyde, we can no longer process it, but it still tastes sweet. So we still get the physical sensation or the physical property of it being sweet. So our artificial sweeteners are a lot of times alcohol sugars. So one of them, I believe they use this a lot in gum, is the sorbitol. Another one they use is xylitol. So notice that the alcohol sugars, I take away the carboxylate, or the C double bond O on top and reduce it to our alcohols. Now another derivative that you may not have known that you were familiar with is a carboxylic acid sugar. So the aldehyde group now is oxidized. So the alcohol sugars, we reduced that aldehyde group. Now with our carboxylic acid sugars, we are oxidizing it to produce a carboxylic acid. So instead of D-glucose, I'm going to have D-gluconic acid. Now one that you actually may be familiar with is tartic acid. Tartic acid is in a lot of fruits. So it's in grapes and bananas and a lot of citrus. But most notably, it's in cream of tartar. So a lot of times if you have like a fish dish, it's a tartic acid. It's cream of tartar that they're using for it. So it is one that we eat fairly often. Interesting, another use of that tartic acid is they actually mix it with sodium bicarbonate. And then they sell it as baking powder. So instead of baking soda, which is sodium bicarbonate, you get baking powder sometimes, and sometimes you need baking powder, especially for making bread. All they do is they take baking soda and add cream of tartar, or add this tartic acid to it, and it's used as a leveling, or used to make the bread rise, and or add bubbles to make things rise in food preparation. Now, just by looking at the derivatives that we were just looking at, we actually saw a lot of the reactions that these monosaccharides can undergo. We saw that those aldehyde and ketone groups can be reduced, or they can be oxidized. So let's go ahead and define all of these reactions now. So we can say the reduction of our C double bond O group in an aldehyde or our ketone will produce alcohol sugars. So whether we have the C double bond O here or the C double bond O here, we're going to oxidize it to produce alcohols instead. Then if we oxidize that aldehyde group, so oxidizing it on top, we're going to get a carboxylic acid. Now we can't oxidize the C double bond O in the ketones here, since that's as far as it can go in the ketone. I don't have another H to be able to add an acid to. So only the aldehyde groups will be oxidized. Now you may be wondering why you can oxidize the aldehyde group on top, but none of these other oxygens are going to get oxidized. So we actually use a special reagent called Benedict's reagent. And with this solution, what it does is it only interacts with the aldehyde up top. So it's actually a copper-based solution, and it reduces the copper from a Cu2 plus to a Cu plus. And so that's why they're a lot of times called reducing sugars, because it can reduce something else, in particular this Benedict's reagent. So a lot of times when you see these monosaccharides being oxidized, you'll always see this Benedict's reagent being used to actually complete the reaction. Now what's kind of cool about this Benedict's reagent is that because it's made of copper, in particular copper 2, it's blue. But since it's being reduced to copper 1, which is a clear solution, we actually know when the reaction is complete because all of the solution turns from blue to clear. Or I guess more of a red-orange, since it's actually a copper oxide that's formed, it's not just the +1. So it goes from a blue to a kind of a red-orange color. Now we're going to be working on a carbohydrates lab, and you'll be actually being able to test some of these reactions in our simulations. So you'll be testing for these reducing sugars, and you'll be adding Benedict's reagent to your test tubes. So that's what you're going to be looking for, is this color change. Also, this test can be used to measure glucose in urine. So you don't want sugar in your urine. It's one of the tests for diabetes, is to see if there's glucose in your urine. If there is, then you have issues with your pancreas and your insulin. So you want to make sure that there is no glucose in your urine. Now, although we said that our ketones can't be oxidized, they can do some fancy organic chemistry and actually rearrange themselves into a aldehyde. So some of these bonds can get moved over, and I produce an OH here, and I get a double bond O up here. Now, if that happens, then these will give a positive result for our Benedict's test. So they will be able to show that there's a reducing sugar in your solution. So we just kind of have to be aware that this can happen. It does not happen in your simulation, but just in case you see it somewhere, these aldehydes can actually rearrange themselves, or these ketones can rearrange themselves into aldehydes. Now, once again, this is an exception, so you won't be tested on this, but once again, it's just something I wanted you to be aware that can occur. Now, you may remember way back in chapter 14, we learned about our acetal and hemiacetal reactions. I told you that they were going to be important in our carbohydrate chapter. Well, here it is. So we said, just as a review, our hemiacetal reactions are produced when an aldehyde reacts with a ketone. Well, what do you know? In our carbohydrates, we have an aldehyde on top, and we have a whole bunch of alcohols in the chain. So they are going to be able to interact with itself and produce our hemiacetal and acetal bonds. So remember, in this reaction, I am taking my H, attaching it to this oxygen, and then whatever is left over, this OR, gets pushed over onto this carbon. So the H goes down, so here's that hydrogen, and this OR gets attached. So a monosaccharide, we said, contains both an alcohol and an aldehyde. So we're going to find that it can actually react with itself to form a cyclic hemiacetal. So we said that OH on the bottom here, that last chiral carbon, this is where our hemiacetal is going to be formed. So this OH here is going to interact with the aldehyde, that first carbon, to form our hemiacetal. But it doesn't look very pretty just drawing a circle or a cyclical chain with a square. So let's actually look at what they're going to look like. Alright, so our Fisher projections are super wonderful to be able to visualize this molecule, but when they actually do mechanisms with how this hemiacetal product is formed, it's not very useful. So I'm going to put it back into kind of our zigzag chain and do our OHs either above or below the chain, depending on where they are in our projection. So I've got them kind of in this circle already. What I'm going to do is I'm going to take this aldehyde here and just move it up a little bit. So when I do, I've got this carbon facing up. So notice this chain is 1, 2, 3, 4, 5, 6. I'm moving that 6th carbon up and moving this hydroxide into that position. Now when I do that, I can see I've got an OH and that aldehyde group. So this H goes onto this O then connects with or bonds with the carbon here. And we get this ring. So that bond goes to the carbon, that hydrogen goes onto our oxygen. Now, because it does matter what side that hydroxide is on, left or right, or in this case, top or bottom, we've got two different molecules. Now, this all came from D-glucose, so we started with D-glucose, but after we make our hemiacetal cyclic compound, we're going to either put a beta or an alpha in front. Beta meaning that the OH ended up on top of the ring, alpha meaning that the OH ended up below the ring. Now, here is some good news. Yay! This mechanism will not be on the exam, so I don't need you to know this exact step by step. But what I do want you to know is that this Fischer projection can go and form these two cyclic monosaccharides. Now, way back in chapter 1, I said that anytime you have a cyclic compound and you need to know whether it's cis or trans or if something's above and below the ring, that you needed to draw our cyclic ring so that the flat side or the horizontal side is facing you instead of drawing it like we normally do with a point facing you, so like this. Remember, if your hexagon was like this, we said it's really difficult to say what is above and below our rings. So we said that we wanted to draw it so the flat side is on the top and the bottom instead of our points. So we do draw it like that. It is given a special name called a Hawthorne projection, so in which the ring is viewed at the side view. So it's this horizontal instead of the pointed vertice that's at you. So the edge or the ring close to the viewer is drawn with a bold line for perspective. So the reason why this is darker is just to show you that if this is flat molecule, this is actually pointed out towards us, the viewer. So our substitutes on the ring of the Hawthorne projection are either up or down. Now notice that we have them up or down here. Remember, there are hydrogens that are not being shown. So there do have to still be 4 carbons associated with or 4 bonds associated with each of these carbons. So I do have hydrogens going up and down, but if we put them, it kind of gets just too messy. So you'll see them at the hemiacetal position, but the rest of the hydrogens are not shown. Also, we notice that, once again, the OH is on top, so it's beta. Here, the OH for the hemiacetal is on the bottom, so it is an alpha. Now, we do give these alpha and beta positions a special name. We're going to call these anomers. So they are still, same number of bonds, same connections, but they are not the same molecule. So because they are not the same molecule, they're an isomer, and the type of isomer in particular is called an anomer. So the A anomer, or alpha, is pointing down. The B anomer, or beta, is pointing up. So these Fischer projections are once again wonderful if we just are looking at one monosaccharide, but we're going to find out that these monosaccharides actually can become or can form longer and longer chains. So the way they form chains is through these cyclic rings. So we're going to see that these alcohol groups now can start interacting with each other and forming long chains for our carbohydrates. Now I do want to go over kind of this mechanism one more time just so that you can really see what's going on and see how I can get from here to here. So I've actually got one that moves for us that we can see, just so we kind of get it in our head of why this can happen. So here we go. So this is where we're going to start with. So we're going to start with the ring formed, but we're going to go back, put it back into our single chain, and then we're going to switch it from this is our beta to our alpha. So if we move it back, so let's go back. I've got this bond here. It's going to move back over, create that double bond. That O goes back onto or the H goes back onto our O. So that's the long chain. Notice now here I've got this aldehyde. this aldehyde, the oxygen could be up top and the H down below, or I could actually flip it. So if I have it up on top, I'm going to form the beta anomer. But if I go back and flip that aldehyde, so notice now the O is on the bottom, the H is on top. When the H from the alcohol comes over and that bond is formed, now I've got the alcohol on the bottom. So this will be our alpha anomer. So it just depends on what position this carbon was in. Was it twisted with the O on top, or was it twisted with the O on the bottom? And whatever chain that gets connected, that's going to stick. Now, as we just saw, it's pretty easy to switch from an alpha to a beta form of our anomers. Now, because it's fairly easy, they actually do go back and forth until they reach equilibrium. So if I start with 100% pure alpha chain, well, if it's 100% pure, it means it's not at equilibrium. So I let the reaction occur, go back and forth a few times until it reaches equilibrium, and then I have some of both my alpha and beta molecules. So because of this back and forth for a little bit, it does change the optical rotation. So initially I'll have one rotation because I have a pure molecule, and as I go back and forth, the rotation changes until I reach equilibrium. So that change in that rotation until I meet equilibrium is called a muta rotation. We don't see this too much, but it's just an interesting byproduct of these open or these cyclic chains that are all in equilibrium with each other. Now, the most common sugars are 5 or 6 membered, or form 5 or 6 membered rings. So because they form 5 or 6 membered rings with a oxygen in the chain, they're actually kind of like our ethers. So some of the names of these carboxylic acid chains, or these carbohydrate chains, actually come from our ether common names of a furan or a pyran. So a furan has the oxygen in the ring for 5-membered, and a pyran has it for our 6-membered rings. These are not names that you need to memorize, but you will encounter them in our chains. So notice that in this alpha D ribo furanose, so it means that it's a 5-membered ring. So basically all of that furanose I want you to get out of it is just to realize that it is a 5-membered ring with the oxygen in the chain. And in this case, the deoxy form is shown since it is our ribose, or our deoxyribose down here. Once again, these long names are not ones that you are going to have to remember, but I do want you to know, or want you to get out of this lecture, is how to name the alpha and the D. So remember how to name the D or the L forms. Notice we've only been doing Ds since we've been looking at organic or biomolecules, because those are the only ones that are going to interact. And then how to identify our alpha and beta rings or cyclic forms. So those are the two main concepts for this lecture. So we'll stop part 2 here. Next time we're going to be looking at our oligosaccharides. So we're going to start actually putting these in chains. So we can see that we've got, once again, all of these oxygens down here, and they can start interacting with other molecules to form our long carbohydrate chains.